out. If any one of you, and I realize a lot of familiar faces here, if you didn't do as well as you thought, yeah, and some, there's reasons for that, and I understand, but if you didn't do as well as you thought, but you really put in a good effort, send me an email, so I can get you extra help, to stimulate. There's so much stuff we can do for you, yeah, so don't be afraid to send me an email and go, Rob, I worked, 30 hours on the last assignment and got a 2. What can we do? Yeah. Although I think that's probably unlikely, right? But yeah. Yeah, absolutely.
All right, get started. Is it showing my stuff? No.
Who's found an error is the survival manual. Yeah, well,
I found another one.
So I remember when I got the survival manual out on Friday afternoon after working all day. It was like late, I think it was like 9 p.m. or something. And I do it, and I'm like, finally I can rest. My partner's about, my future wife's about to divorce me. We're not even married yet. It's like, Rob, stop the work. And then like Serge sends me like 7 messages on the Slack, and he's like, I think this is an error, so I go and fix it. And he's like, no, you still have an error here. So Serge is leading with like 4 or 5 like just minor typos. Things like nothing game breaking. But I might have a prize for the person who finds the most at the end of the semester. There should be a lot of typos in there or minor things that don't feel right, yeah? Like, everything will work, but if you see these things, like, oh, should variables just be variable? Or like, you said that you're plotting it in green, but it, in the code it comes out blue.
Do you want us to like annotate it and I'll send you the PDF?
Yeah. Yeah, it'll get you in the thanks at the bottom.
Yeah,
I don't know what the price is yet. It won't be like a trip to the Caribbean or anything.
Automatic 7.
And it won't be an automatic 7. Are we ready to go, Yulin? I'm just providing the
thanks.
show entertainment here. I'm the opening act. And the closing act. Yeah.
Thanks, Rob. All right, good morning, everyone. Morning. My bus took me 1 hour to travel 6 kilometers. Okay, so today is for the simple linear regression in R. We have some people online. Can people online hear me? Yes, probably. So have you received my email yesterday about the workbook? So basically, that's the kind of a code you can copy and paste. Oh, no, you can't copy and paste. You have to do some modification for today's activities. So basically,
can I mention something?
Yeah.
This work's just going to be me jumping in occasionally.
Yeah.
So I said to you, Lynn, it's like, rather than just show them the code, we want to get you the skills to do the PST. So I said, it has about, we show you how to do something, and then make you do that exact same thing on a different data set and deal with all the minor differences. So this is why we have Lydia along, because we'll all have problems trying to do the minor differences on different sets. So it'll be you demonstrating, and then you doing it.
Okay. So as you know, simple linear regression is the foundation of all statistical models, I guess, machine learning. Today's machine learning, like a kind of a popular word. Doing your stuff again?
You always see this happen, you go, doesn't this person know how to use a computer? But then when you end up with
look at those two.
nothing works, trust me.
So basically, first of all, you have to specify your model. So basically, you have to figure out which one is the X variable or predictor, which one is the Y variable or outcome or dependent variable. And then we estimate the model using a statistical package. For example, the package is in R. And then we have to check the assumptions, because every single model, statistical model, has a set of assumptions. If the assumptions are satisfied, we can go ahead to interpret the results. If the assumptions are violated, we have to judge how much is violated. If it's just slightly violated, maybe you can still go ahead. If it's a very heavily violated, we have to probably re-specify the model, or maybe just choose a different model and then redo everything again, because if the assumptions are violated, the results are not accurate or not available, reliable. Okay, and then once we confirm the assumptions are okay, and then we go to interpret the results. For simple linear regression and most regression models, we can even make use of it. We can make predictions in new situations. Okay. Okay. So today's work is like this one. So you see the code. You see the examples in the workbook. That is based on the Gapminder data we used last time. If you were here last time for the data visualization session, and then we can use the code to work on some new data. So basically, this data set is about the demonstration data set is the one you said last time. It's about the population features in the last 70 years in different countries across the world. So in the demonstration, I used the GDP per capita to predict life expectancy. Okay, so you can see this is the demonstration data set. And then we are going to use the same code to work on a different data set, which is in this one. Empty cars. It is a very small data set for teaching purpose in R package. So we're going to predict which one? We're going to predict fuel efficiency using the car weight. Okay, some cars are heavy, some cars are light. So we're going to try if we can use simple linear regression to predict the fuel efficiency based on car weight. The fuel efficiency is measured by miles per gallon. That's a USA data, so it's get some funny measurement units, miles per gallon. Weight is in tons. I guess in tons. Oh no, 1,000 pounds. Oh, anyway, don't worry about that.
This data set's also used in the week 11 lectures. So we actually we use in the week 11 lectures we use automatic or manual or the number of cylinders. Week 11 is about categorical variables. So this is kind of nice. You get it with a continuous variable here, and then if you see this week's lectures, you'll see it done with categorical variables.
Yeah. So this data set is used in week 11 lecture as well. Okay. So let's get started first. So first of all, you should see the bookmarks in your PDF I sent you yesterday. So first one is to check the data. So in the demonstration data set, we did this. So first of all, we get the data out from the package called the Gapminder. So we assign the data set into an object called the demonstration data. You can call it whatever you like. And then we can view the data set by running view demo data. You can see this part of the data set. I'm pretty sure you can do this from so far in week 10. Again, all right, in this data set, we have a 1,704 observations. And then we can have a quick view of the data. So STR stands for structure of the data set name. You can see the data set, you can see the variables, their types. Some are factors, some are integers, some are numerical, and then their values. And we can have a quick summary of data set. You can see the summary statistics if the variable is numerical. You can also see the frequency table if the variable is factor. Okay, yeah. So you should do the same thing for the empty cars, the practical data set. Okay, I call this one practical data. You can see the practical data. So first of all, you need to know how to use GG pairs to have a quick overview of everything. GG pairs.
So if you just run what Julian has there, the say function GG pairs not found, what do you need to do first?
Yes,
so
yes,
you want to have the GG ally package installed.
Yeah, I forgot this one. Sorry.
Oh yes, up there.
So first of all, if you check your workbook, first of all, get ready for the R session. Install the packages you have if you haven't, and then load the packages, because these are the packages we have to use on top of the base R functions. Gapminder, ggalley, tidyverse ggplot, and then boom. Okay, yeah. So first task is to have try to get the GG pairs out of the empty cars. And Lydia, maybe we can work around. If you have any question, just raise your hand. We can help out. Yeah. For people online.
So remember the GG pairs, and I showed this last week in the interactive lecture. The GG pairs function gives you like this pair plot and correlations for all pairs of variables, right? Now you want to be careful because if you have a data set that's enormous, running GG pairs will try to make a billion things and your computer might crash, right? So what Yulin's done there is he's created a new object which has just the names of the columns he's interested in, and you use that as the second argument to the GG pairs function, and it only plots those ones.
Yes, yes.
So I'm not sure if you necessarily, I think you might need that for your PST too, but generally that's a good one to know. If you have a million things, then obviously you crash and you use GG. Okay?
Yes, it's a good practice. For this data set and also for the empty cars, it probably doesn't matter because we only have a few columns. But in your real life of a researcher, you may have a huge data set of 1,000 columns. You don't want to do that for GG pairs. So you just want to choose the, yes, I deal with some data set with 1,000 columns.
1,000 is nothing, but you have data that's collected now. Every time you buy something on Amazon, right?
Yeah.
Time, date, item, user ID, previous history, etc. This is how Amazon gets so good at predicting what you're going to buy. And this is also how Facebook gets so good at making oddly weird suggestions. Yeah? I don't know if people still use Facebook. Showing that I'm general right here. But does TikTok have ads?
TikTok.
Yeah. Are they strangely like accurate about what, like you're talking about a dog and next thing you know, like selling dog things?
Like a chihuahua here.
Yeah. Facebook does that. It's creepy. I'm talking using Facebook.
Yeah.
But it's because you have all this data, right?
Any problem with GG pairs? So far?
We'll walk around and we'll have a look.
All
Make
good?
sure everyone can do this.
Okay. All right. So if you have any questions with GG pairs, just let us know. We move to the next step. Next one.
You've all got it, right? Everyone got the GG pairs going? No? You're in. Let's go around the room for 5 minutes and
Okay.
help. Yeah.
Okay. Sure.
All right. So who was it on? Yeah. That's it. Yeah. Let's have a look. So you've got one variable. Do you want to have one variable? Well, not one variable, but like 1%. Yeah. So that's fine. Usually the reason you use this is you want to show everything off.
Oh, no, no. I don't know my actual.
Yeah, good idea.
So see, these are the variables. So with this one, you can basically not try to get a vector of things you're interested in. But for example,
I don't know how to do
But anyways, for this, I need to know that this was the distinction between those features. Like you have to learn on top of it.
So if you've already got it, while we're helping everyone else, try doing a GG pairs of only the variables WT, MPG, QSEC, and FRAC.
Yeah, if you want to work on your PST2 data, it's fine. You're welcome to do it. Okay. Yeah.
Just a quick question. Like the last one was section 3.
Any questions from people online?
Okay, so you've done library alone, right? So you've loaded up library.
So first of all, you have to install those packages if you haven't. And then for today, you have to use the library function to call them out for you to use it in this session, okay? Yeah.
Yeah, but that's just the function.
Okay.
But what you want to do is you want to give it information. And so what's the name of the data?
Much better at that.
Really
Okay. This sounds good. So after GG pairs, we can see that you know, the diagonal shows the histogram with a density plot, the density curves, and then the lower triangle of the matrix shows the scatter plots, and the upper triangle shows the correlation coefficient. Okay. Yeah. Okay, let's move on to data exploration. So remember, in my demonstration, I am trying to predict life expectancy using GDP per capita. Therefore, I plot a histogram for each of the two variables separately. So this is the code for histogram of the dependent variable, life expectancy. Now, in your practice today, we are going to predict fuel efficiency MPG using car weight WT. So you should make a histogram for MPG and a histogram for WT. So you can just use this code here, and this ggplot data set is for you should be the practical data set, empty cars. And then the axis should be the variable name, either WT or MPG. The geom is histogram. And I also add a density curve on top of the histogram, if you can see that, a red density curve. Yeah, so if you can try to replicate this example, but using a different data set. If you want, you can also work on a PST2 data if you like, no problem. Yeah.
Testing.
Yeah.
So you all would have done plots like this if this is 100% new to you. I think one of the computer labs, I think like computer lab 5 or 6 probably took you through how to do those sort of plots. Maybe 2.
Okay. So you can see in this data set, the MPG, minor data set, the variable life expectancy seems to be bimodal, right? It has 2 peaks, a lower peak and a high peak. And this is the second graph. This is the histogram of the GDP per capita. Yeah. GDP per person. So you can see it's highly skewed to the, is it skewed to the left or right?
I always get them around the wrong way.
Skewed to the left or right, Lisa? Huh? Right, yeah. The skewness is about the tail. The barbecue skew is about the pointing. Huh? Yeah. By the way, the definition of skewness is very awkward. I think there's some paper talking about we change definition or maybe just each fall, but this. Yeah.
So they're now going to do that for which variable in the empty car set, Ewan?
So for empty car set, because we are predicting MPG using WT, so you have to plot a histogram for MPG and a histogram for WT. MPG is the miles per gallon,
WT is the car weight.
Cool. Let's give you a few minutes to do that.
Yeah, we'll work around.
Don't be afraid to kind of put your hand up, yeah? Histograms of MPG and WT.
Any question for people online?
And just having a histogram isn't good enough. It needs to be a good looking one, right? So if you have like bins in weird positions, yeah, maybe you want to use the num bins argument. Yeah.
Good education.
Oh goodness.
Yeah, not bad. Yeah.
Just changing state, changing that. Which variables are we pressing about?
MPG and WT.
And for anyone that's successfully done it and waiting, I would challenge you to make the histogram look even better. Hints, you can use fill and color to basically put the line around it. This is just if you're waiting. Otherwise, you're just going to walk around and make sure everyone else has actually got the histogram.
Nothing's working, James. I'm trying to give it to you. No, so the should be having the email for workshop.
I'll just add it in anyway.
Yeah, just try it. White against the
MPG. I actually think I saw the work. Like, you know, just going around and Nick, it'll be on Blackboard in like 10 seconds. Yeah?
Have you done
Yes.
Yeah.
But a lot, like a few years ago.
Yeah, I did it.
If you have a look on Blackboard where the survival manual is, there's the second link of it. Yeah.
I tried it. What did you do? Did you work it? Did you figure out? It was
Oh.
which part do you think?
You're next on the list of questions I'm answering. It's an argument for AES and the geohist.
I don't think it's good. It's under geohistory.
Yeah, so it's an argument for geohist.
Yeah.
Oh,
Yeah. Have a look at the survival manual. See, there's a demo in there.
okay,
Okay,
cheers.
so the issue is when
Okay. So if your histogram doesn't look perfect, so many gaps, that means you have to.
you want to write the code for the answer for the empty cars data set. So if anyone did a do it, can see what.
Oh, okay. Yeah. So basically, let me copy my data first.
Yeah, no, I remember. Yeah. Doesn't look the best, but you know.
To be honest, I think it's scrambled because it's horrible. Putting the extra line in there.
Okay, so I want a histogram of as an MPG. So I just copy my code from my workbook, or you can copy it from the survival menu. So, oh, sorry, have to get things ready first. So library them out.
Okay, so have a look at the survival manual.
Okay, so ggplot. First of all, you tell the ggplot your data set. So my data is equal to preg data. And then the variable I'm going to histogram is called mpg. Okay.
Yeah,
I think that's the only thing you have to do. Just change your variable name and the data set name.
This is a recurring theme, right?
Give it a try.
You look at code that works and then work out what you want to do to change it. Yeah? So this is why we gave you the survival manual, because you can see all these demos of things that work, and then you just need to change it to do what you want to do.
Yeah. Oh, that's what I do basically. I'm not a super expert in R, so I just whenever I need it, I just Google and then find example and then just copy and paste and modify the things until I get what I want. All right, let's keep going. All good? Okay. So of course, in your PST, you have to also comment on the data, on the results, on the graph, whatever you get from up. You can't just show up the graph. You have to give some interpretation, right? Like this one is highly skewed to the right. Definitely not normally distributed. Okay. The last, not the last one. The next one, which is kind of relevant to your PST2 tasks, is to request some XY plot or scatter plot of the two variables of interest. So in this demonstration, because I was trying to predict life expectancy using GDP per capita, so I request an XY plot or scatter plot of these two variables. I put the variable that I'm going to predict on the vertical axis, and then put the predictor, the variable I'm using to predict
on the horizontal axis. So in your practice today, you are going to predict mpg, miles per gallon, using WT, car weight. So you need to figure out which one you put on the x-axis and which one you put on the y-axis.
It's a one-way ticket to not getting marks if you don't put your explanatory variable on the x-axis. But more important than marks, you will lose all credibility with your fellow scientists if you put your outcome variable on the x and your predictor on the y, right? It's just standard practice that the explanatory goes on the x and the outcome goes on the y, right? So please never forget that.
Yes, it's just convention, yeah. It's just convention. I guess in your PST2, you have to plot a series of scatter plots until you find a linear trend, right? Yeah. So if you have any trouble with this one, just raise your hand. We'll work around to help you. It looks good, yeah, pretty linear.
If it's easy for you to do this, and you've already done it, because obviously we're going to help you for 4 or 5 minutes, try to make the points blue.
Yeah. Yeah. By referring Rob's survival menu.
Or maybe you just remember how to do it. I mean, you've been practicing in the workshops for like 10 weeks now.
Or just Google if you like. And obviously you can see this one. It doesn't show a linear relation. So how to interpret a scatter plot? I guess you have to mention probably 3 to 4 things. First of all, you need to check if the data shows a relationship. If the data just shows a random ball of points, it means no relationship. Anything non-random, that means there is a relationship. So first of all, you need to judge if the data shows some relationships, some non-randomness, okay? And then, if the relationship is monotonic, I mean positive or negative, okay? This one is definitely not random, so there is a relationship. No metric. There is a relationship, and it's kind of a positive, because as the x variable goes up, the y variable also tends to go up. And then the shape of the relationship. So this one is not linear, right? It's curved. It's curved. And then the strength. How strong is the relationship? I guess this one is not too bad, because you can see the points are kind of closely clustered around the trend line, although the trend line is not linear, but there's a trend line. So we have a kind of a positive non-linear, probably moderate to strong relationship in this scatter plot. So when you are writing your PST, make sure you write something out of it.
So if you remember, and I'll talk more about this in interactive lecture today, but if you remember, we always talk about assumptions, right? Yeah. Now, you can fit a line through anything you want, right? It doesn't really take any assumptions. You can always find the best straight line that goes through that data, right? Your assumptions will be invalid because the residuals aren't around the line, they're centered at 0, and the error won't be normal, right? You can always fit a line through something. What the importance of the assumptions is for when you do hypothesis tests, right? So that's the key thing you need to remember. Like, the assumptions are there just so hypothesis tests are justified, okay? That's why, and also it's probably a bad model if you fit a straight line through it and the residuals have an S shape or a U shape, as we saw in the week 10 lectures.
Okay. Now, because I
observed a nonlinear relationship in the previous graph, so I gave a try. I tried in this one. I tried to take the natural logarithm of the independent variable. Because why? Because remember previously on the histogram, I noticed that GDP per capita is highly skewed to the right. So one way to rectify right skewed or positively skewed variable is to take the logarithm and then the most commonly used days is the natural days. So there's no firm rule, just kind of, okay. I take the logarithm of the x variable, and then I plot the log transformed GDP per capita against the original life expectancy. So this time, we can obviously see a positive relationship. It's kind of linear, and then it's kind of moderate to strong because the points are closely scattered around the trend line. But we also notice a little kind of annoying thing. These 5 or 6 points kind of outlying out of the bulk of the data set. So you can consider them as outliers. But the definition of outlier, I guess, depends more on the substantive meaning of the observations rather than just the data. But based on the histogram, based on the scatter plot, we can see that those 6 observations are lying out of the bulk. So
you got 2 options there, right? Either those are outliers, in fact, like data that there's something odd about. So I think some people, if you looked at your CSA, you would notice, you might be in the room actually, you notice like someone's like, I think like for one of the data points, the columns are swapped. Like it said like someone's height was like 50 centimeters and their age was 173. So whenever you see data that's kind of a bit strange, you want to ask yourself, is that an outlier that I should get rid of? Maybe something wrong has happened there, yeah? So there's 2 possibilities here. As Yulin said, like, you've got data that doesn't work with linearity, so you've got 2 options. Either that data is just erroneous in some way, okay, like there's an error, or like the model does not make sense to extrapolate past kind of the point where the data starts behaving weird. And I think, Yulin, we're taking the second approach here. We're saying, okay, well, we're going to discard that data and only use our model on the area we know it looks linear. Does that make sense?
Yeah.
Cool.
You can also do some sensitivity analysis. So you can compare the results, weights and result of special ones, see how much the results change. Yeah. But anyway, in your practice as a scientist, you have to pay some attention to outliers because sometimes there could be the where you make the breakthrough in the science, some special new species or something. Okay, so don't just delete them because all the data are collected with money and time. They are all expensive data. All right, so what I did is just kind of simple. I just let me get rid of those special ones and then plot the data again. So basically, based on the histogram you see before, I see that anything above 5,000 is probably too high, too rich, those countries. So I just I just remove them from this plot. You can see here. First of all, I use a filter vocabulary from tidyverse. Use a filter. I filter out the data that has GDP per capita less than 50 grand per person, and then I assign this new data set. I call it demonstration data part, and then I use the partial data, the part of the data to plot the histogram and the scatter plot again. So make sure you try this one again, and then we will come around and help you. Yeah. So I also request a trend line, and I also request a linear best line of fit. So you can see these 2 lines are almost the same. That means my relationship in this scatter plot is very, very linear, very linear. Right?
No, so the important thing to notice with this is with filter. So you remember from like week 1, who remembers what filter does? You get a subset. Yeah? Nice. Yes, correct. Can someone give me a slightly more descriptive thing though?
You can pick out the variables you want to measure and graph.
Yeah, you can pick out kind of, it basically shows you the data you want to see, right? So filter, I remember, is the command that says, show me only the data that satisfies these conditions, right? So here, where Yulin's written demo data set is filter demo data GDP per cap less than 50,000. This means demo data part is going to be a new data frame, which is demo data, but anything that's where the GDP's not less than 50,000 is not there. It takes it out. So try to do a pair plot with the straight line kind of best fit through it. So the method equals LM. For the case study, the MPG versus, what are we doing? MPG versus WT? Yeah. Yep.
Yeah, so you should be trying to conduct a similar sort of, like, you're going to explain kind of what he's done here and his reasoning. We want to do pretty much exactly that.
I've also done this too.
Yeah, nice.
Yeah. Split it out by the
No challenge. Was it not was it? You tell me. I'm asking you just a reaction. So, what did you feel about?
this I didn't like the way to apply the max variable at the very end. So it's 5 plus 5, so 5 plus 4, so that's my string.
Yeah. Now, can you show me the whole data? So you shouldn't just toss out data because occasionally it's like, okay, if you describe linearly in a certain area, if you what might be better here is for a number or things like that, right? But you're right, it's a tough one. Yeah? Okay. So like if you want to fit a pure straight line, then you want to say, yeah, it only makes sense to do that. Yeah? But generally you want to be careful throwing out data. Like if something's non-linear outside of the set, then you want to ask, is there another model?
Any question for people online?
But no.
I'll get rid of that and put it in the poly.
Okay. So I guess in your PST, you are requested to explore the data by transform X or Y or both of them until you observe a linear trend, and you can stop.
That's consistent.
Well, this is the thing. You don't really discuss much more likely to introduce what's around this. Yeah? It's really got two sides. Oh, yeah, so you want, anytime you want to remove outliers, so there's a reason to do it. Yeah. One reason is you only care about predicting in a certain range, and it looks beautifully linear in that range, and so on. I'm never going to want to predict out there, I don't care. Yeah, but then you got to admit the limitation of your model. Yeah. So, yeah, so I mean, what you was demonstrating is that sometimes linear is a really good model, but only up to a certain point. But if you're actually interested scientifically in everything, then you might want to ask yourself.
Okay.
Well, I talk all about that.
So in this example, I didn't change the Y variable. I only log transformed the X variable. In your PST, I guess you have to try 4 combinations: original X and Y, original Y versus log X, original X versus log Y, and log X versus log Y. Which one looks most linear? You have the judgment. Okay? I can't tell you, but one of the 4 combinations will look the most linear in your PST2 data. Okay. Yeah. The reason we want to see a log, we want to see a linear trend line because so far in SEB 113, we have only learned how to estimate and interpret a linear model. That's why we want a linear relationship.
Assuming you're only up to week 8. In week 10 we do polynomials.
Yeah. So if you know, definitely there are possible ways to do it. So once we know how to estimate and interpret nonlinear models, we don't have to request a linear relationship. But so far, we only learn how to interpret a linear relationship. That's why we request we want to see a linear pattern. And then we can apply the statistical model, the linear regression model, in the linear data to get the results. We keep going? Okay, good.
Does anyone have any questions or still has issues?
Good. All right. This one is not perfect. So if you want to make a graph perfect, you should label the x and y properly. How to do that? We did that last time. You can also refer to the survival manual, how to label the x and y properly, the variable name, and also the measurement unit. My current this demonstration doesn't look perfect, okay, in terms of the x and y labels.
No full marks for you, Lynn.
Yeah.
In this case. So x lab and y lab, yeah? So those two?
Yeah, label of them. Okay, now we finished the first step, data propagation. We come to the second step, model, and the third step, model estimation and assumption verification. To estimate a linear regression model in R grammar or R language is very simple. So this is the code. So the function is called the LM. LM, I guess, stands for linear model. And then you tell the data equal to your data set name. And then you put a dependent variable, the y variable, and then a tilde, a squiggle line, and then you put an independent variable in here. If you have more than one independent variables, which you will learn very soon, you have to plus second variable plus the third variable. But for this week, it's only one x variable, so just one thing after the tilde. And then after that, we're going to assign this model estimation based on this data set into a new object. We call this my model. You can name it whatever you like, okay?
The LM function is the most important thing in your life now. Like the rest of, not only for this PST, but like the rest of this unit, everything is just through the LM function. That tells you how to specify a model. All that changes, so everything you're seeing us do today, and more in the interactive lecture, is the same sort of thing. Explore your data, see how you're going to make a model, tell R to make a model, and see if there's evidence that certain aspects of those models should be left there or taken away. Okay? The only thing that changes in the next 2 or 3 weeks, everything from this is week 8 stuff, I believe. Everything that changes from week 8 to week 13 is just the type of variable and how many variables are in your model. Okay, so it's worth really getting this LM stuff. So stop and ask us if you're like, I don't even understand what this function means. We're more than happy to go through that more. Cheers.
Has everyone got the linear function estimated? Yeah. So basically, the model specification refers to this part. That's the specification of your model, the x variable and the y variable, and how do we combine them? We combine them linearly.
It's a very weird way of typing in the formula of your model, right? Because we teach you that squiggly line means has distribution in like week 7, right? And that's not what it means there. So basically that life x tilde log is R speak for my y variable is life x, and the formula for the model I have is equal to that variable there plus an intercept. There's always like an intercept term hidden in there. So yes, you're not alone if you think it's weird the way. If it was up to me, the way I would work is you would type life x equals beta naught plus log GDP per cap plus times beta 1, and then it would know what everything needs to be from that. But R's not that smart, and very few things are. But no, so you've got to specify that there. So
Someone got it? Like,
Okay. Yeah. So after estimating the linear model using the data set, you have to verify the assumptions of a simple linear regression. There are a set of assumptions of simple linear regression. Check the details in your lecture slides. And I read some books. Some books tell me there are 7 assumptions. Some books tell me there are 5 assumptions. So anyway, I guess the assumptions include that, first of all, the relationship between x and y has to be a linear relationship in order for the results to make sense. Because what we are interested in most cases is the slope or gradient of the linear trend line, of interest. And how do we interpret that? We interpret that as the marginal effect of x on y. So as x increased by 1 unit, we are interested in how much on average y would increase. Okay. But if the relationship is not linear, that interpretation doesn't hold anymore. So first of all, we have to remember that xy has to have a linear relationship. You can check that using the scatter plot. We did that before already. And second, and the other assumptions around the simple linear regression model they are basically all around the error term, the epsilon, the error term. Remember, the model is that y equal to beta 0 plus beta 1 times x plus error term epsilon. And most other assumptions are all around the epsilon. So if we assume that epsilon is a normally distributed, with a mean of 0, and a constant variance at different levels of y. So we have we assume that this kind of a vibration or weight around the trend line is kind of equal from low to high. You can see this one is probably not perfect because the dispersion of the points is a bit wider when the y is low and becomes more concentrated when the y is high. So it's not perfect, but not too bad. Why do we need that? Because only when the variance is constant or homoscedastic, then the p-value comes from the estimation will be 100% reliable. If the variance of the error term is not homogeneous or homoscedastic, then we have to be cautious about the p-value. Right? Okay, so we are sure that the relationship is linear because of the scatter plot we have done. And then now we're going to verify assumptions through residue analysis, basically through the graphical analysis of residues. So first of all, we have to get the residues out. So this is the code here. So we use the fortify function. I guess it's from the Broom package, B-R-O-O-M. So you have already installed and the library of the Broom package. Now we're going to use the fortify function to consolidate the residue stuff. So it's very simple. So fortify the model object and then assign the fortified model outcomes into a new object. I call this one my model.fort. You can name it whatever you like as long as you remember what it means. If you don't remember, just make some notes, annotation using the hashtag.
The great thing about the fortify is, if you wanted to, you could actually do the predictions and make a column with hat, and you could compute the residuals by taking the data away from predictions, and then standardize them. But the great thing about fortify is it does all that for you, right? Okay. I don't know why they call it fortify, but it certainly saves a lot of time. So it's very important.
Get this one out, please, using your practical data or PST2 data if you like. Fortify. The first column is the y variable. Second column is the x variable. The dot hat, as is a measure of the observation in terms of the x variable. If the hat is very high, that means the x value is very different from the others, from the average.
Isn't it just a prediction?
No. The prediction is a fitting.
Oh, sorry, yes.
Yeah,
Of course.
yeah. Dot hat, I guess, is the measure of leverage. I don't know if you...
Ignore the dot hat then, yeah? It's not equal to y hat in our notation.
Yeah. For sigma, I guess, is the... what's dot sigma?
Honestly, I'm not too sure.
Dot sigma.
The ones we know about are fitted and .std resid, right? So fitted are basically the fitted values of the line of those points, and the std resid is the standardized residual.
Dot fit, that is the prediction of the dependent variable based on the independent variable and the regression function we estimated. So that's the value of the y variable on the trend line. That's dot fit. That's the one you are interested in, the y hat. And this is the residue, and the last one is the standardized residue. Dot sigma, I think something about the error term estimate.
I need to check because
Yeah,
it's not an estimate of the variance of the residuals.
No, it's not residual. Sigma, I think, is the standard error without that row of observation. I guess, but doesn't matter. I don't think it's relevant to a PST2. And dot Cook, this one is a Cook distance. It's a measure of the influence of the observation. So if the observation is very dominating the data set, it will have a high Cook distance. But anyway, for your PST2, the most important things are the last three columns. The y hat, the fitted value of the y residue, and the standardized residue. Also work around, see if you can get the results.
If you can get that table easily using Fortify, I would encourage you to try to create that table without the things you don't care about. See if you can figure out how to do that. Kid, you use the select command. Yeah. Just display that table without sigma or Cook SD or hat.
Yeah, so what way is the explanatory resource of the x-axis? Yeah, so that's fine. And then miles per gallon is so that's correct, yes. So try to create a new one now using select. This is just my sneaky way of making use of which is maybe using CSA. The last one is the ones you care about. So which ones do you know what they are? Resid and standardized resid, right? Yeah. In fact, you probably want LifeX and log GDP, right? So LifeX and log GDP. So log GDP is a predictor. LifeX, does that matter? Oh, so you're doing a different. Yeah. So you want to only show kind of the explanatory variable. So the explanatory variable and the And the cool thing about select is you can actually choose the order in which it shows it. So it makes more sense to have explanatory miles per gallon. It's also nice because it often argues you weight of information and half the time you don't fully understand. Like you look at glance, right? Anytime you glance at a model, you get AIC, BIC, log life. I don't know what those things are that you don't, right? So when you write a report, it maybe doesn't make sense to include like useless information, so you can actually just say show me this subset of columns. Yeah, there you go. That's what I was saying. Yeah. So it's just kind of practice at using select. Yeah. And the cool thing about select is you can change the order of things if you want, right? So weight is actually your explanatory variable. Yeah. So basically, I would probably put weight first, and then miles per gallon, and then fitted. So fitted's next to miles per gallon, so you can see how close the fit got. Yeah. Because then it becomes obvious how you get resid because it's just one of it minus the other one, right? Yeah. Although why? Oh yes, this one minus this one. It's exactly this one. Yeah. So see how that kind of communicates the same information, but in a way that makes it easier to kind of grasp? So, what's wrong?
This concrete. It's not enough.
You need 5 minutes.
What?
Do you need 5 minutes?
Sorry?
Do you need 5 minutes to go get something to eat? I'll give you 5 minutes.
There's not much else we have to do.
It's so much better when you can only show the data than the table. Oh, yeah.
Yes, I am. I'm just blind. Oh, Charlie. Oh no. I have some aesthetics. Is it? That's MATLAB now. Yes. Yeah.
Okay.
Ask you on MATLAb.
Okay, now once we get the residues, we are going to verify the assumptions by analyzing the residues. As I mentioned, most of the assumptions are around the residue term. So first of all, we need to assess if we can assume that the error term follows a normal distribution. How can we do that? We can have a look at the residues, because we can use residues as as a measure of the error term, because error term is an error term you can never see, is unobservable, but we can guess about them by looking at the residues. Okay. So how to assess if a variable follows a normal distribution? We can request a histogram, okay, to see if it's a bell shape distributed. And then, so now it's just a histogram of the residue term. I use the standardized residue because I'm going to compare the standardized residues histogram against a standardized normal distribution curve.
That's very important. Anytime you do a QQ plot, which is coming next, you must use the standardized residuals. Yeah?
Mm-hmm.
Because you're comparing the QQ plots against the normal 0, 1. Yeah? If you don't standardize your residuals, you're doing it against the probably normal 0 sigma squared. Right.
Yeah. So this is a histogram of the standardized residue, but it's a special one because on top of the density curve, the red one, I also overlay a blue curve, which is the Z distribution curve or standard normal distribution curve. So that's how you can do this one. So this part.
Excuse me.
This line, ST80 step function dot geom function equal to standard norm. That is the line you need to draw this additional blue curve, because the blue curve illustrating the standard normal distribution. So ideally, I would expect the blue curve and the red curve to match each other or something, override. But you can see there's a little bit discrepancy, but not too bad, not too bad. I think practically, if the sample size is large enough, we can kind of ignore the assumption of normal distribution.
No. Not with linear regression, right? So Euler's thinking about central limit theorem. Yeah. So when you're doing a test of population means with 7 or 8 stuff, then central limit theorem says you don't really need to matter if things are individually normal. I mean, this normality is an assumption, doesn't matter how much data you've got. And I'll talk more about that in the interactive lecture. It's a bit complicated, so I'm going to discuss it more at length there.
Okay, have a try of this one, so you can get the histogram. Any question? No question? Let's see people online. We have a question about from Chris online, how to plot two series on the X sim X and Y plot. Which one did you, can you write a bit more about that, Chris? So another way to check the normal distribution assumption is to plot your data against normal distribution. So basically, the QQ plot is the QQ quantile plot of the standardized residue against the quantiles of a standard normal distribution. So this is how we get a QQ plot using ggplot. But I know there are other packages in R you can request QQ plot. Straightforward. But I guess
this is pretty straightforward. You just copy our code and change the name of the variable. That's really
So basically for PSD2 we have to do this way.
So remember, like you do fortify, you pick your model and you do fortify. Okay, and that gives you the standardized residuals. Yeah. And then you get the code for doing the QQ plot, which is that code there. And I think in like the week 8 lecture we kind of took you through what each part of that code means. But the important thing is just understanding that that will do, as long as you give it standardized residuals, that will give you the QQ plot. Yeah. There are other functions in R that can do it, but we only wanted you to learn one way of doing it, because instead of 50. And this is the way that looks the best. So. Also, we understand that, yeah, this ggplot stuff is hard, right? But the only way it gets easier is by doing a lot of it. That's why, like, we try to do everything with ggplot, because the more you see it, the more you get used to it.
Okay, then we'll try this one here. So I have a look at it. So, Chris, which one? You mean the scatter plot? Or histogram?
So we'll get everyone to do it for your cars data set. Try to do a QQ plot residuals of your standardized residuals. In fact, try to do a QQ plot where you use your actual residuals and not the standardized ones, and have a look at how funky that looks.
So the good thing of using ggplot is to it shows you understand what ggplot means, the content plot. Yes, it's easier to guess the plot from using other packages, but because we are learning the theory in SP103, that's why we require you to use ggplot to understand the meaning of content plot. So basically, we are comparing the quantiles of the standard normal distribution against the quantiles we estimated from the column of standardized residues from the 45 data set. So if the quantiles, they all match, if the quantiles match exactly, you can imagine the QQ plot will show a 45-degree straight line, right? For example, the quantiles of 5% of the standard normal distribution is negative 1.64 something.
Around there.
Yeah, 644, 6445. And if the quantiles of the column of standardized residue is also negative 1.6 something, that means it's a perfect match. And if all the quantiles match each other between the theoretical quantiles and observed quantiles, and then we would expect a 45-degree straight line. So if you look at this one, the data shows kind of linear trend. And that means the shape of distribution is not much too different from a normal distribution, specifically from standard normal distribution.
Remember my tip. So I mean, everything you're seeing today we've done before. This is more like revision or catch up if you're falling a bit behind. But if you remember my interactive lecture from a few weeks ago, I said like these can be a bit hard to interpret exactly like what it means if part of it's underneath the line, and I did some examples there. But the general rule is you want those dots close to the line, right? If those dots like fall off the line in a very structured way, then you're like, okay, this probably isn't normal. Something like that, it's like probably close enough. Yeah, you want to do this diagnostic just to make sure you don't have something crazy, right? So those dots when they're like in an S curve around the line, that's clearly indicative of something being wrong, right? But something that lies roughly on the line, we notice that towards the far end, on the left and the right, it falls off the line. This means that the tails are either squished in or stretched out more than a normal. But generally, and that's exactly what we're seeing there, the right-hand side squished in, the left-hand side's pulled out.
You can compare this histogram of standard residues against the QQ plot of standard residues. Because it's not perfectly standard normally distributed, the QQ plot is not perfectly straight. So you can see we have some skewness. Okay. So hopefully the QQ plot of your data set will look okay. And then we can go ahead to verify other assumptions. Otherwise, you have to consider transform your data or maybe using a different model. The next residue plot is the residue against the predicted value or residue against the fitted value. So it's just a just a simple scatter plot, but we put the standardized residue on the Y, and we put the fitted value, the prediction of the dependent variable, on the horizontal axis. And what they prefer to see is a horizontal band of points with no obvious trend, and they also prefer to see the band base is kind of equal from left to right. Yeah. If you see any trend, positive linear trend, positive trend or negative trend, that means you probably missed a variable in the specification. And if you see some curve trend, that means probably the relationship is not linear. And then if the vertical spread is not equal from left to right, that means the assumption of homoscedasticity or homogeneity invariance of the residue is probably violated. So this one, we don't see any trend. We see a horizontal band, but the vertical spread is a little bit different. The spread when the fitted value is low is a bit wider, and the vertical spread on the right-hand side when the fitted value is higher is a bit narrower. So a little bit violation, but I guess it's judgmental here.
So all models are wrong, right? This is the thing you got to remember, all models are wrong, but you want to see if the assumptions of your model are roughly satisfied, right? Because when you do these hypothesis tests, and I'm going to talk more about this at 11, when you do these hypothesis tests, it's based on the assumptions, right? And who thinks these assumptions are kind of weird, like come out of nowhere? So why do we need to do these strange things? At 11, I'll talk about it. We'll look at the mathematical formula for your linear model, and I'll show you exactly how these assumptions are actually obvious and staring at you in the face there. I thought they were very weird myself. So why do we need this from the skin? I said, why do we need this? But when you look at the model, it's actually quite clear, and we'll talk about that in a little bit. But for now, I want you to try to do one of those plots for your data, MPG versus WT.
Because the empty cast data set is very small, only 30-something observations, so the plot doesn't look easy as we normally see. It's very simple plot, only a few points. Yeah. It's for teaching purpose. That are simple. So it's just a simple scatter plot. You specify the data set, which is my model.fault, the x variable, the y variable. I use the geom point. I use alpha equal to 0.3 because I want to make the point a little bit translucent or transparent. And then you label, this time I label my x and y properly. So I'm expecting a full mark for this plot. So you label them, x label, y label. So make sure you do the same thing. When you are plotting something, you label them properly. And then I request smooth trend line, and then I request the background to be black and white. And then I didn't request the interval around trend line, so the SE is a false. In the geom smooth trend line, I don't really want it. What's that called? Interval around trend line, so I make it false. So it's just a simple trend line.
Yeah, for this it doesn't really make sense to do confidence intervals. You just want a smooth line fit through the data so you can see if that line. So it's like with the QQ plot, right? If you have that diagonal line in the QQ plot, points on the line good, points off the line indicative, maybe not what your assumptions are saying. It's the same with this. If that smooth line is perfectly flat on 0, that's a really good sign. But if they're not, then it's a worry. But in this case, it looks like it's reasonably satisfying. Because remember, your data's random, right? Or it's modeled as random. So if you had an infinite amount of points, if the assumption was verified, that line would be perfectly straight.
Yeah.
But given we only have a smallish amount of points, it seems to be reasonably straight enough. I'd be happy with that. What do you think?
This is very important plot. So we can, because based on this result plot, we can check a few assumptions. So we can check the linearity assumption. So if you see any nonlinear trend line, then is the linearity assumption between x, y is violated. And if you see any trend, positive or negative trend, then you have a missing variable in your prediction. And we can also check the homoscedasticity, the vertical spread from left to right. We can also check the potential outliers. So basically, remember, if the residue is super large or super small, then means the observation is very far away from the trend line. So we can measure that using standardized residue. So if the standardized residue is above 3 or below -3 something, that means that observation is very, very far away from the trend line. So it's a kind of special point.
At 11, I'm going to actually generate some data that doesn't satisfy the assumptions, and we'll have a look at what the different lines you get look like. Because sometimes, it's one thing to say, oh, if it satisfies it, it's this, but it's really good to see what it looks like when it doesn't satisfy and to identify those patterns. So you will see more of that.
Yeah, thanks. Okay, let's move to the next section, model results interpretation. So now, once we confirm that the assumptions are okay, we can go ahead to interpret the results. Okay, because we know that the results should be accurate and reliable once the assumptions are met. So first of all, there are different ways to request the output. So you can use glance. I think glance is part of tidy words. So glance and then broom. Part of broom. So glance and then put your model result object in the brackets. You can get a little table of the R square, adjusted R square, sigma is the estimate of the standard deviation of the error term, and then what's the statistic? It's probably F something. Yeah.
Yeah, so in the glance table, R squared is the R squared value, which we all know what it is from lectures. Adjusted R squared, don't worry about in this unit. Sigma is the standard deviation of the residuals from memory. Statistic is the test statistic. So it's just, that's something that you know the distribution of in H0 world, but you don't need to use it because R uses the test statistic to give you the p-value, so it does it in the background for you. The p-value is the p-value of a hypothesis test for the whole model versus some baseline model. So the baseline model in this case is just without, like, just an intercept instead of an intercept plus beta 1 times something else. Yeah. And the DF degrees of freedom and the rest are stuff you don't need to worry about in this unit.
Yeah, so this statistic p-value and DF, I think that's refers to ANOVA of the regression, I guess, which they don't really care about.
Yeah, ignore that one.
And the other things like the model fit measures like BI, CI, CBS, again, they are of the same purpose, I guess, as R squared, different formulas, which we can ignore for now. Yeah, so I guess you want to get, I guess, the most important you want to get out of is R squared. You can also, the one I prefer is the summary function, because that is the base function in R. You don't have to install anything to get it. So summary and the model name, we can get this model specification, the residues measure, and then the estimates of the intercept and the slope, the standard error of intercept slope estimate, the t-value, because we can perform t-test of each of the parameter we estimate, and the two-tailed p-value of those parameter estimate. Remember, the p-value here is always two-tailed p-value. You may or may not want to use a two-tailed p-value. So if you want to use one-tailed p-value, you can divide this p-value by 2, you get a one-tailed p-value. That depends on your hypothesis in your research question. Okay, and then here we get the again, this is the standard error. Yes, standard error of the regression, which is the standard deviation of the residue. And the degree of freedom of the simple linear regression is a sample size -1 minus number of predictors. So in simple linear regression, we only have one predictor, so samples -1, which is samples -2. And then the R square, is R square here?
Multiple R squared.
Multiple R squared here, it's same as this one, 0.6658.
And the F statistic is, that's week 11 stuff. So F statistic you can do for more than just simple linear regression, but it works with simple linear regression as well. But for now, you don't need to worry about F statistic.
You imagine that in next week, no? In
so this week's lectures.
In multiple regression, Rob will mention the F test. Yeah, so I guess it's an easy way to.
But for simple linear regression with one predictor, F test and T test give you the same answer.
Yeah, just look at the p-value here. The F test p-value is exactly the same as the p-value of the estimation of the slope, because the F test is testing if the hypothesized regression coefficients are 0 or not, which is the same as we're testing here in the T test. But in this way, when we have more than one X variables, the F test is testing if all the regression coefficients, if all the slopes are simultaneously equal or not, which is different from the single T test for each single regression coefficient, right? We can also use this one tidy to get the confidence interval. I guess we need this one for DST2 for the confidence intervals of the intercept and slope. So if you want a 95% confidence interval, you just have to specify the level of confidence to 0.95. Okay, so how to interpret the results? It says, based on the sample data I have, I guess the intercept estimate is about negative 10.6, and the slope estimate is about 8.6. That means it's a bit hard to interpret here because I log transform the GDP. So that means if the log transform is GDP is 0, then I would expect the life expectancy to be negative 10. Statistically, it makes sense, but practically, it doesn't make sense because nobody lives negative 10 years old. So that's why we normally don't care about the intercept, but we do care about the slope. It tells us as the log transform GDP increase by 1 unit, I guess it's $1,000 US dollar. Is it 1 or 1,000? I can't remember. Then the associated increase, because okay, the associated increase of the life expectancy on average is 8.6 years.
And I'm going to stop you in there. See, so that's why units are important. People always say in this unit, there's another one. It's like, why do we need to always include units on things, right? You don't want to get units wrong, yeah? You don't want to say like the GDP of a country is, 50,000.
Let me have a picture.
It's probably like 50,000 million or something, right?
Not this one.
And this is doubly important in this CSA. You're not going to have a good time if your units are wrong. And the best way to check if the units are right, rather than looking at the data that comes from your data set, is think to yourself, does this make sense? Right? If you have height data for people, it's probably not 173 meters. No one's that tall, right?
Yeah, this dollar, just US dollar. Yeah. Okay, and definitely need this output, confidence interval for PST2, and then make the correct interpretation. Yeah. And then okay, this is the one again relevant to our PST2. So these t-tests and the p-values, they are testing the hypothesis that the intercept is 0 or the slope is 0. Sometimes we want to test a hypothesis about a specific value which is not 0. The package doesn't give you that test result automatically, but we can do it manually. So suppose we want to test if the slope is equal to 10 years or not. Then the hypothesized theta 1 will be 10 rather than 0. And then we can manually calculate the t-score, which is the sample estimate of the slope. Lowercase b1, in this case, will be 8.6 years per dollar, minus the hypothesized value, in case it's 10, I put 8.6 here for b1, and then minus 10 for beta 1. And the whole difference divided by the standard error of the estimate. The standard error is given to you here, is negative, is 0.148. And then that t-score, when the assumptions are met, is supposed to follow a t-distribution with degree of freedom equal to sample size minus 2. In this case, is a 1696. And then I can use the t probability function in R to request the p-value. Okay, if my t-score is a positive, this function tells you the cumulative probability of a t-value, which is from here, and given the degrees of freedom. So the cumulative probability is always from left to the point. So if my t-score is positive, you should take that out of 100% because you're after the right tail p. And if my t-score is negative, you can use this one directly. That will give you the left tail p. And if you want a two-tail p-value, you have to multiply the one-tail p times 2. Okay. I can't tell more because that will give you the answer to my PhD2, but that's the code you need to use. Okay.
Yes.
It's a t probability distribution of a t-value.
But I will give you a way to know if you're doing the right thing-ish, right? So notice as Yulin said, like that you need to compute it this way if you want to do a hypothesis test to see if the true parameter is different from some hypothesized value, right? Now, if that hypothesized value is 0, R does it for us, right? Yeah, when you go up to that table here, the p-value it shows in that table is that the beta 1 connected to log GDP per capita is doing the hypothesis test for whether or not that's equal to 0, right? So if you use the formula and follow the procedure Yulin just gave you should get a similar answer by setting beta 1 equals 0, because you're just doing what R is doing by hand. Yeah, so if you get a number that's not smaller than 2 times 10 to the power of negative 16, that's what e negative 16 means, 10 to the power of negative 16. You get, like, say, a value of like 0.3, you know you have computed the problem. Yeah, so you've got the answer already for when beta 1 equals 0. So you want to make sure your answers match up in the same range, and then you want to do it for a different one. Because remember, your PSD2 asks you, is the Moore's law coefficient different from the value you've been assigned in your individualized student data, right? Yeah? No, I'm not going to say anymore.
Yeah, so you have to figure out what's the value of beta 1 you are going to test for yourself, because each person is given a different value to test against. But you have to do some log transformation in your PSD2, it's not. We don't give you the value to test against directly, we give you something and then you log transform it.
We do want to make you think a little bit. We can't just have you show up to this and then copy the code and change the name of the variable and everyone gets 4 marks. I'm sorry.
All right, now we come to the last step. So I guess we probably have to work around to have this part. So we can, once we get a regression model, estimation of regression model, we use the regression function to make predictions. The regression function is y hat is equal to beta 0 hat plus beta 1 hat times whatever x variable you observe in a scenario. So now we can make a prediction of the life expectancy given the observations of GDP per capita, and then have to use this predict function to make a prediction. So first of all, I just created a new data set of the GDP per capita. So it's a single column from 500 to 50,000 spaced by 1,000. So I have a single column of GDP per capita. Smallest one is 500, the largest one is 50,000, and then by every 1,000 I pick a value. It's a kind of a hypothetical data set. Now I'm going to predict the life expectancy for each single observation in the new data set, because I know the GDP per capita, and I use the model that we just predicted before. So this is how you make a prediction. Okay. You can also request prediction interval and the confidence interval of the conditional mean. So here I just make the prediction and then also request the 95% prediction interval of individual cases. And then I make another one, which I make a prediction and then also request the confidence interval of the conditional mean. And then I consolidate them and then I visualize them in the end, which is this one. So make sure you try this one before we go, and then we will work around and help you. Okay. So ideally we want this data set. The x variable, the predicted y variable using our model, and then the prediction interval 2 columns, lower bound, upper bound, and then confidence interval, lower bound, upper bound. And then we use this diagram to show that the predictions and the confidence interval, which is the very narrow blue band, and the prediction interval, which is the very wide pink band, because the prediction interval is always wider than confidence interval, right? Because it's always harder to predict individuals than predict the average, given the x.
Yeah, so that's discussed in detail in the week 10 lectures, if you need to go back and refer to that.
Okay.
And it also shouldn't be surprising that all the predictions, all the dots there that you plotted were on the line, right? because the line is exactly our model for the means. For a given x, that the mean is given by the line, so of course that's our prediction. Yeah.
Okay, we'll work around to help you with last week, because do we need this for the PSD2?
You need this for life as a scientist, which is strongly correlated to what you need in the assessment for this unit. So whether or not it's in PSD2, I can't remember, but CSA, you probably will need this.
Yes, yes. All right.
I always have my smart answer to that question, right? That's
So I'll try and use the why the other one is
Yeah, so glance and tidy and tidy, there's no group. Yeah, I'll try and go. Go to low room, yeah? Oh.
That's one of
Alright, install the import.
Did you get my book?
Yeah. I was ready, and that's fine with me. Yeah, follow. You just didn't have it. So it was probably looking for an old version or something.
I know, I'm measure it, but that was good. You guys.
Yeah, so the hypothesis test of the cumulative multiplier as the value of the test existing on this given equation. Now, what expression means is yeah, it's expected value of as it's green, we multiply the or to the same thing on the left. Yeah, or that's yeah, absolutely. That's what we say times two. Yeah. So you just compute one side. Yeah. Yep. No, so in your case, the null hypothesis would be that it's equal to 3. That's what you want to test against. You want to say, is there evidence that not is true? Yeah. So this is why because what R does is usually that's what you're interested in. You're saying yeah, but in your assessment it's pretty different. It's that that's what you're saying. It's nice, it's a bit tricky actually that we make it do at this point. But as I said, if you computed this, you would see it would match the T in if you computed up from beta 1 equals 0, it would match the yeah.
when you
So this is saying that so it's running the simulator with take one parameter and get this. But just look at this now without getting this essentially is this is telling you that that's the p-value R, that's the beta. Yeah. So the whole thing with like checking these functions, you assume you're saying you're assuming that the actual relationship is some line with error.
Yeah.
You're assuming that you're assuming plus now, what the what's the same thing? Well, the evidence that the truth is what oh, exactly.
It's already okay in the last
They said that like he was, but you would have an appreciation. And then that's true, that's what you're wrong. But you would have an appreciation that one percent of the power making 50 should probably be considered more equitable than 0.0499999. You know? But that's like the reason they have that is they just fundamentally it doesn't matter, and it's fine. Let's look at levels say 7. Yep. Now, if it's very, very small numbers, then that's sense overwhelming sort of evidence. But at the end of the day, that what that number is shouldn't really matter because you could say that numbers. But you would understand science and other people that tells you something, right?
So since you guys in the room, so if you have a 1 minute or two, just log your attendance, please, and then also give us some feedback to online forms.
So this one's for you, Nick, that feedback. The feedback for me is the student voice. So that one is kind of you, Nick.
Yeah, I will email you the links as well later today. And we also have something for you. You may like to have no, I guess work for you already, right? This one?
Yeah. So I'll talk about this in the interactive lecture. But,
you have the slide.
They've got another workshop coming up which might be useful for your CSA.
Yeah,
it's about actual writing, scientific writing.
We're working on that. But we have this time slot you can use for booking your consultation with my colleagues about academic writing, either online or in library. This is the link, and anyway, you get a copy of this slide from Rob.
For sure.
Yeah, okay.
Okay, thanks everyone. I'm going to duck out for a bathroom break because I'm back to the Rob show at 11. I hope you stay for it. We're going to discuss more about like what these assumptions mean and why we need to check them, and this helps you understand what all these weird tables are saying. But this last session has been focused mostly on how to accomplish the things you need to accomplish in R, but we're going to talk about really understanding them in 10 minutes or so time.
Thanks, Julie, mate. I've got to duck off. I'm done.
Yeah, sure. I'm picking up too. So I just leave it open for you?
Surely.
Okay, any question from people online before we conclude? All right, thank you very much. See you next time.
Yeah.